Yeah, this is a short video to talk about what to do with forces in a mechanics context. This is an abbreviated conversation just to talk about how you deal with resultant forces and acceleration. So here's an example. Suppose you have two forces F and G that are acting on some object that has mass 2 kilograms. Calculate the magnitude and the direction of the acceleration of the object. Okay, so the idea here is that we need the resultant force. So the resultant force is the sum of all the forces acting on the object. So in this case, it's F plus G. And when you have vectors in I and J notation, Cartesian notation, you add the I components and you add the J components. And it's because forces in perpendicular directions don't interfere with each other. So your resultant force is, so to write it all out in full, we're adding those two forces, but you add the I components, and that gives you minus 5I. And you add the J components, and that gives you plus 12J. So this is your resultant force. I'm just going to call it R for resultant. You can call it whatever you want to call it. That's where we end up for the resultant force. Okay. And the relationship between force and acceleration and mass, well, that's Newton's second law. That's force equals ma, or rather the sum of the forces equals mass times acceleration. So we know that the sum of the forces was minus 5I add 12J. And we're told that the mass of the object is 2 kilograms. So that's 2 times whatever the acceleration is. Acceleration is a vector quantity, just like force is a vector. Mass is a scalar. Mass doesn't have a direction. It has a magnitude. It tells you how much, 2 kilograms, but it doesn't tell you what direction. So mass is a scalar quantity, and so we can have a scalar times a vector. And to solve for this vector A, I have an equation. I can divide both sides by 2, and I divide both those suckers by 2. So I've got minus 5 halves I plus 6J is my resultant acceleration vector. Okay. And if I want the magnitude of that thing, the magnitude of a vector, sometimes we notate it like that. The modulus symbols mean magnitude. Side note, when you learn modulus with numbers, like if I say the modulus of -7, we say just whatever it was, strip off the negative and take the positive version. That's true, that's a correct thing to say, but a more complete thing to say would be modulus means take the magnitude. And the magnitude is how big. I don't care about direction. So -7 on the number line is 70 units away from 0. So the magnitude of this number is just 7. So the magnitude of this vector is how long is this vector? So we've got Pythagoras, and you might have done enough now to know that you're going to do this to get the magnitude of your vector. But it comes from Pythagoras. So this is Cartesian form. So if I slap this on the grid, well, I go over 6. Oops, excuse me, that's not right. I go back minus 5 halves units in the x direction and up 6 units in the j direction. So this is my resultant vector. And the magnitude of that thing, well, I've got Pythagoras. That side is 6, this side is 5 halves. I guess we didn't need to throw the minuses, but I'm using the numbers that they gave me, just to be clear. And that's going to take you to, I know you're ahead of me in your calculator, and you should come up with some horrible number. Maybe it's not that horrible. Minus 5 halves squared plus 36 square root. Oh, that's not bad. That's not bad. That's going to be a 13/2. you work with these numbers long enough, you learn your square roots. So 13 over 2 is the magnitude of my acceleration, and I suppose that's meters per second squared because acceleration. Okay, and the direction of the acceleration, well, direction is often expressed as an angle. So this is my resultant acceleration vector. And I need to describe where it's pointing. And I can use all kinds of angles on this picture. I could use that like a standard position kind of angle. I could use the angle it makes with the y-axis. I could use the angle it makes with the negative x-axis. I could use its bearing if I'm taking positive up as north. Billions of ways to describe the direction of a vector. What you need to do is just make it clear what you're doing. And I'm a big fan of right triangles, so I'm going to go with the angle it makes with the negative x-axis. But as long as you're clear with your picture or with your written description, you're okay, and exam board should accept what you do. Okay, so this angle, that's tangent. So the tangent, and I don't really care about how this angle is. Well, I mean, I'm going to say that this vector makes an angle of that much with the negative x-axis. So those words will tell me how this triangle is situated. To work out this angle with tangent, I'm just going to take the positive lengths because I'm just thinking of a triangle. I'm not thinking of being on the grid just to get that angle. I realize I've drawn that the wrong way around. Okay, if this doesn't make sense, please drop me a note. So the tangent of my mystery angle is opposite over adjacent. So I guess that's 6 times 2/5. That's 12/5. Okay, and my angle is inverse tangent of 12/5, which in degrees shakes out as, how many decimal places do you care about? 6, 7? I'll go with 1. So we'll say 67.4 degrees. And it's important that you say degrees because in year 2 of A-level, you learn about measuring angles in radians, and then it becomes mission critical what setting you're in, whether you're in degrees or whether you're in radians. So always, always mark degrees, and there you go. So my picture shows what angle I'm after, but I could say the acceleration makes an angle of 67.4 degrees with the negative x-axis. Okay, and that's clear from my picture that I mean this angle sitting up here and not the angle, I guess I could say makes an angle of 67.4 degrees above. That's better, above the x-axis, so I know I'm sitting up here and not down here in the third quadrant. Okay, so that's how you play with mass and acceleration when they give you a question like that. Okay, I'd like to do another scenario, which is a little bit, can you see through that? You can see through that, which is a little bit different. Okay, and it goes like so. Suppose you have 3 forces acting on a body of mass 5 kilograms. In nearly all of these mechanics questions that you do, the object that has a forces acting on it is going to be a point mass. That's not a realistic real world concept, but for modeling the math and the mechanics, it's fine because you're learning concepts. You're not trying to be real world specific. I know that objects have dimensions and mass and different bits, and that if I suppose I'm pulling my rock like this, I mean, it might break down the middle. Real world objects do that kind of thing. But in math, we pretend that we've got a point mass. Okay, so a body of mass 5 kilograms. Okay, and we've got 3 forces acting on it. So here's the first force in Cartesian form. For I, whoops, minus 3j. Pay attention to what I've written down over here. These are my cheat notes. Okay, well, I'll write it out nicely for you. For I, minus 3j, and my second force is some mystery quantity of i's plus 5j's, and my third force is 10 i's plus some mystery quantity of j's. So I've got an unknown in my second force and an unknown in my third force. These three forces are acting on my object. My mass is 5 kilograms. Okay, m is 5 kilograms. Okay, and I know that the resulting acceleration shakes out to be 3i add 2j. How do I know that? I just made it up. I scribbled out some numbers that seem to work nicely ahead of time, and I'm asking you to work backwards to figure out a and b. So sometimes the how come for these problems is because we wrote it that way. But it's helping you practice the concepts and the skills and the algebra of it all. Okay, so I haven't given you a question yet. My question, first of all, is work out a and b. So the first thing I care about is working out the values of a and b. So the sum of your forces is mass times acceleration. So I need to add all my forces up, and I can do this adding the vectors like I did before. Sometimes you want to yank things apart into what's happening in the horizontal and do that separately. And then you want to look at what's happening in the vertical, and you look at that separately. And sometimes, that's appropriate, and we want to do that. And you can generally do that whenever you've got Cartesian vectors. You can separate them out, but you don't always have to. And basically what it means is you're running things in parallel. And this is what I mean. So my three forces all added up together is going to be mass times whatever my acceleration vector is. All right, so I've got 4i, oops, I really want to add that 3j. 4i minus 3j, add ai, add 5j, add 10i, add bj. When I do that, I get 5 times my acceleration vector, which is 3i, add 2j. And again, mass is a scalar, so I can multiply that through my acceleration vector. Okay, so if you're happy to hear, okay, what I'm going to do on the left-hand side is I'm going to collect up the i's and write that, and then I'll collect up the j's and write that, just like we collect like terms with any other variable. I and j aren't variables, but we can collect them up in a similar manner. And over here, I'll distribute the 5 through. So I'll say 15i plus 10j. All right, so these are the i's. The i's have it. So I've got 4 plus 10, that's 14 plus a. So I've got 14 plus a worth of I. And you can do that. You can group your addition as a coefficient on your unit I vector. And same thing with the j's. And I find it really helpful to, mark out the terms I'm looking at so I don't miss anybody and I don't mix them up. So minus 3 add 5, that's 2 plus b. So 2 add b worth of j. And that's going to give me 15i plus 10j. Now at this point, what we do is we equate coefficients. And this is a popular technique in all kinds of contexts in mathematics. But if I've got a pile of i's and j's over on the left and a pile of i's and j's over on the right, then I should have the same amount of i's and the same amount of j's. So what this means is 14 plus a ought to be 15. And that tells me that the value of a is 1. And likewise, 2 plus b better be 10, which means that b is 8. Okay, so I figured out the values of a and b. Yippee! Okay, and that's practice in the sum of the forces is mass times acceleration, and it's practice in your vector notation. And that was the point of that question. Okay, and then the second thing I care about is a little bit more to the story. Okay, so the story then goes, a fourth force. I'm modeling this on existing exam questions, by the way. The fourth force is now acting on the mass as well. So I've got all 4 forces in play. Okay, and the upshot of this fourth force is that the acceleration is now 0. So the forces are balanced. or you could say that the forces are in equilibrium. Okay. You only get an acceleration when there is a force applied. If something is accelerating, then there is a force acting on that object. If you have no forces acting on it, or if the forces are balanced, so they cancel each other out, then you don't have any acceleration. You might still have velocity. You might still be moving, but you just won't be speeding up or slowing down. The acceleration doesn't mean zero velocity necessarily. It could. I mean, you could be absolutely stationary, but you could also be moving at constant velocity with zero acceleration. Okay, so the question is work out your fourth force. Tell me the description of it in I and J. I could say what's the magnitude of it. I could say what's the magnitude and direction of it. You know, we could pick these vectors apart all day, but right now I just care what the force is. So this means that when you add your forces up, mass times acceleration, but acceleration is 0. So I need to work out that mystery force. So I know what F1 is. That was 4I minus 3J. I know what F2 is because I know that A was 1. So it's 1I plus 5J. And I know what F3 is because we worked out that B was 8. So it's 10I plus 8J. Plus 10I plus 8J equals, plus our mystery force equals 0. Okay, so all of this says 4 plus 1 is 5, plus 10 is 15, 15I minus 3, add 5, that's 2, add 8, that's 10, plus F4 equals 0. And then if I subtract, if I subtract these two terms to the other side, subtract these two terms from both sides of the equation, I can see that my fourth force is going to be minus 15I minus 10J. And there we are. Okay, I hope that was helpful, and I hope that helps you through the rest of the exam questions. All right, thanks for watching.